Hello, I welcome you all to your own channel MSK Learnium. Now, in this video, we are going to discuss about the new chapter that's name is the simple steam power plant. Right? So you know that whatever the power we are generating means the electricity we are getting, that power we are generating from the thermal power plant means majority of the electricity is generated from thermal power plant also. Right? So the thermal power plant is also known as the steam power plant. So this is the video that totally we will see the basics that how the steam power plant is functioning, means how to get the efficiencies of a plant, right, and which thermodynamic cycles is follow in a steam power plant, right, for a for electricity generation. Also we will see the schematic layout of a steam power plant and some parameters. So first of all we will start that what are the main component of any steam power plant, right. So if you see the steam power plant, the main component is boiler, turbine, condensers, feed water pump, electric generator, cooling tower, circulating water pump, chimneys and draught system. So one by one we will discuss. So first of all we can say the main component of steam power plant, that is steam power plant in short we can say SSPP, right. In short you can say SSPP means simple steam power plant. Right. Now the main component of any simple steam power plant you can write that main component of steam power plant, that is simple steam power plant, SSPP. Right. Main component of simple steam power plant. What are the main component of simple steam power plant? We will see here. First you can say the turbine. First you have a boiler. Okay. First you have a boiler with its mounting and accessories. Mounting and accessories is nothing but the additional component which is used in boiler to perform their efficiencies, right. So we can say boiler with its mounting and accessories. Boiler with its mounting, okay, and accessories. Boiler, you know, that is in which the steam is generated when your heat is supplied, right. The second one you have a turbine, that in which the steam will expanded and the work is produced. The third you can say condenser, where the heat is rejected and the steam is condensed, the means vapor will be converted into liquid. Fourth you have a feed water pump. You all please copy this simultaneously. So you can say feed water pump, that which is used to feed the water to the boiler from the condenser, right. Fifth one we have a electric generator, where the electricity will be produced, means mechanical energy is converted into electrical energy. So this next you have a electric generator. Then you have a cooling tower, right. So which is connected with the condenser, cooling tower, right. Next you have a circulating water pump, that which is from the condenser to the pump, right. So you can say circulating water pump, right, water pump. Next you have a chimney, that why? Because the steam is generated. For generation of steam the heat is required. It means that combustion will do the combustion. So when the combustion will takes place, the smoke will generate, right. To release the smoke we are mounting the chimney. So next you have that is chimney. And ninth one you can say this is draught system. And last you have a feed water treatment plant. Okay, feed water treatment plant. So in any simple steam power plant you have a basic main 10 component will be there, that boiler with its mounting and accessories, turbine, condenser, feed water pump, electric generator, cooling tower, circulating water pump, chimney, draught system, feed water treatment plant, right. Now we will see that how the steam power plant is functioning. So for that we have to draw the schematic layout of a steam power plant and then we'll try to understand. So let's do that. First of all, simply you can draw one schematic layout of a steam power plant. Very nicely you can draw. So here we go, just wait, yes. So now we are drawing the steam power plant, that is schematic layout of a steam power plant, right? So you can make a note that schematic diagram of simple steam power plant, that is of SSPP, right? So here you have a boiler. Let's say this is your boiler, right? And here you have a turbine. First I'll draw everything, every component, and then I'll connect them, right? So this is the turbine. Next you have a let's say this is the condenser. Here we have a condenser, right? And here we have a pump. Here we have a pump. Now we can arrange them, that these are arranged like this. So from here to this is the exit of the boiler, and this is the inlet of the turbine, right? Inlet of the turbine. And again from here, this is the exit of the turbine, and this will be the inlet of the condenser, right? And this is the exit of the condenser, and it will be the inlet of the pump, right? And then this is the exit of the pump, and from this it will be fed to the boiler, right? So the direction of flow, that fluid will be flowing like this. This is like this, this is like this, this is like this. Is it or not? So in this, in power plant, if you look at that, the phase has changed, means liquid to vapor and vapor to liquid. Right now, that is phase transformation will take place. But if you remember that when you studied about the gas turbine plant, so in gas turbine plant, the phase is not changed. Means throughout the cycle, the liquid working fluid is in the gaseous state only. But in this steam power plant, the fluid working fluid is in the liquid to vapor and vapor to liquid, means the phase will be changed. So now here you can say this is your boiler, right? This is the boiler, you can mention. This is your turbine, means this one is the turbine, and here you have a condenser, you can write, and this is the pump, right? And here this, with this turbine, the generator is coupled, right? This is the generator is coupled by means of the turbine. Now, so what will happen, that say that this is the inlet of the exit of the boiler 1, right? And this is the inlet of the turbine 2, exit of the turbine 3, right? And exit of the condenser 4, and this is the exit of the pump. So what will happen, the fluid is circulating, right? Means from the liquid to vapor and vapor to liquid. First of all, that the liquid is fed by the pump to the boiler. In boiler we are supplying the heat. So because of the heat generation, because of the heat supplied, the steam will be generated, which is having high pressure, high temperature. The high pressure, high temperature steam will enter into the turbine. It will strike with the turbine blades. The thrust will create, the work will develop, right? Or the steam is expanded partially. So when it is expanded partially, the work has produced, and because of the spinning of the shaft, that EMF is produced, and that from that EMF the electricity will be generated. After expansion, the steam is entered into the condenser. Here that water cooled condenser or air cooled condenser you may use, right? So the chilled water is circulating into this. If it is the water cooled condenser, when the steam is entered into this, the heat will be rejected, and this steam, that expanded steam, is converted into liquid, and then it will be fed to the pump, and from pump it will further fed to the boiler, and then the cycle will be repeated. So if you see here, from here, means at the exit of the condenser to the inlet of the boiler, the fluid is in the liquid state, and from here, that exit of the boiler to the inlet of the turbine, it is in the vapor state. That is means it is a steam, and from the exit of the turbine to the inlet of the condenser, it is in the mixture, that is liquid plus vapor, right? So this is how the steam power plant, simple steam power plant, is working. Now we will see some performance parameter of vapor power cycle, right? So you can write next that performance parameter of vapor power cycle. So we can see here that performance, make a subheading, that performance parameter, wait, that performance parameter of vapor power cycle, right? That is vapor power cycle in the sense that a steam power plant also, right? That is vapor power cycle. Don't be confused with the steam power plant, right? Same only. Okay, so first performance parameter, we will see that what is the thermal efficiency. So efficiency, you know, output by input. So first parameter you can write, that is the thermal efficiency. So we have a thermal efficiency. All right, thermal efficiency. So in short, you can denote this neta th, right? So thermal efficiency is what? The thermal efficiency of a plant is, you can define that net work output by heat supplied, right? So you can say thermal efficiency of any plant, NTH, neta th is equal to net work done in the cycle by heat supplied in the cycle. So we can say net work done in the cycle by heat supplied in the cycle, by heat supplied, okay, in the cycle. So you can write like this also, that thermal efficiency neta th is equal to W net work by heat supplied, that is Q in. So this is what you will get. Net work you can find by turbine work minus pump work, and heat supplied, you are supplying the heat to the boiler, right, for generation, means at the time of combustion. Next performance parameter which we will see, that is our, see the performance parameter, we already written that notes. So next performance parameter, we have a back work ratio, right? So very first you can write the second performance parameter is nothing but back work ratio. One we already discussed, that is thermal efficiency, no problem, right? Sometimes it happens that we don't follow the sequence actually right now. So back work ratio we can say in short, you can denote BWR, right? That is back work ratio. So back work ratio is what? Pump work by turbine work. So you can say back work ratio is equal to the ratio of pump work, right, by turbine work, all right. So you can say here that here itself only we can write, so this is what? WP pump work by WT, that is turbine work. So this is how you will get the back work ratio, right? That is simply the ratio of the pump work to the turbine work is your back work ratio. Next we will see the work ratio. Next performance parameter of vapor power cycle is work ratio. Next you can write, that is the work ratio, okay. Next we can say work ratio. So work ratio you can denote WR in short. So work ratio we can say the work ratio is equal to net work output by turbine work, right? So we can say the net work output, and these all net work output in a power plant, that is in a steam power plant right now. Net work output by turbine work is your work ratio, is the by turbine work. So you can say the work ratio is the simply the ratio of net work output to the turbine work, or you can say WR means work ratio is equal to W net work output by WT, that is turbine work. All right, then next we have a performance parameter is steam rate, right? Next performance parameter you can say that is the steam rate. So here we can explain that is a steam rate. Steam rate means what? At what rate the steam is consumed. So we can say steam rate is also called as the specific steam consumption, or it relates the power output to the amount of steam necessary to produce it, right? So for power output means it's telling that means steam rate will decide that what will be the power of a plant, right? Means how much output will get from the plant, that will be decided by the steam rate only, right? So you can say it is also also called as specific steam consumption, right? Specific steam consumption, consumption, or we can say that it is the amount of steam required to produce 1 kilowatt hour of power, or you can, in another way you can say it is the amount of steam required to produce 1 kilowatt hour, means 3600 kilojoule of power, right? 1 kilowatt hour of power, right, of power. Or we can say it is denoted by SSC, that is specific steam consumption. So you can make, that is, it is denoted by SSC, specific steam consumption, right? So specific steam consumption or a steam rate we can define now, that is mathematically specific steam consumption is equal to mass of steam in kilogram per hour by power output, that is whatever the output you are getting, means turbine work minus pump work, you can say power output. All right, that is in kilowatt you have to take. So this is how you will calculate the specific steam consumption in any power plant, right? That is mass of steam in kilogram per hour by power output. Mass of steam in kilogram per hour means what? In 1 hour how much steam is flowing into the plant, and power output is the work, net work, you can say. Then you have one more performance parameter which we have to discuss, that is our heat rate, right? So you can say, just hold on, yes. So next performance parameter we have a heat rate. So please just hold on. Yes, so next performance parameter we have a heat rate, right? Heat rate. So that next performance parameter we can say amount of heat required by a power plant to produce 1 kilowatt hour of power. So we can say it is the amount of heat required by a power plant to produce 1 kilowatt hour of power, right? So you can say heat rate, that is heat rate HR is equal to 3600 by thermal efficiency, okay, thermal efficiency. So simply you can say heat input, or you can say this is heat rate, that unit will be the kilojoule per kilowatt hour, right? Or another way you can say that heat rate is equal to heat input means heat supplied, right? Heat input by net power output, okay. So this is how we can get the heat rate. So heat input you will take in kilojoule per second and into 3600 also, that is into 3600, right, by net power output. So this is how we will get the heat rate. So these are the performance parameter in any simple steam power plant. Now we will see one simple numerical problem based on this discussion. So that will be brush up our discussion. So now the question is on the screen, please see that here. You can wait. Yes. So the question is that if power developed by a turbine in a certain plant is 1200 kilowatt. So this is the power produced by the turbine is 1200 kilowatt. Heat supplied to boiler is 3360 kilojoule per kg, means heat we are supplying to the boiler is this much, and the heat rejected by steam to cooling water means heat rejected from the condenser is this much, right? And the feed pump work required to condensate back into boiler is 6 kilowatt. So the pump, means pump is a power absorbing device, right? Pump, compressor, power absorbing device. So we have to give the work to the pump. So how much work is required? 6 kilowatt to feed the water, right? So we have to calculate the mass flow rate through the cycle. So what is the mass flow rate through the cycle? We have to calculate. So first of all, you can say the power turbine work is given. Pump work, what is the pump required? Work is required to run the pump, that is given 6 kilowatt. Heat supplied is given, heat rejection is given. So when we calculate the mass flow rate, right? Mass flow rate throughout the cycle means we can calculate the net work in kilowatt by net work in kilojoule per kg, right? So net work in kilowatt you can calculate from the turbine work and from the pump work. Net work means what? The total work produced, power output is 1200. From this output, how much work is required to means we are giving the work we are giving to the pump, that is 6 kilowatt. So remaining work after giving this, that is our net work, and the heat supplied is this much and heat rejection is this much. So we can get this. So first of all, we can calculate net work, that you can say solution. Okay, solution, and given data you have, that is given data. What are the given data you have? Let's say that is turbine work, I am denoting this WT, it is 1200 kilowatt, right? And WP, that is pump work, is 6 kilowatt, it is required, right? So actually you can say this, we are feeding the work to the pump, right? So this we can take a sign convention as a minus also, right? Why? Because work is done on the system is negative. Then heat supplied, you have a heat supplied QS is equal to 3360 kilojoule per kg, right? And the heat rejection, that QR is equal to 2520 kilojoule per kg, right? First of all, what we will do, we will calculate the net work in kilowatt and then net work in kilojoule per kg. So first I am calculating the W net, okay, in bracket you can write in kilowatt. So it is what? Turbine work minus pump work. So turbine work you have a 1200 minus 6, which is 1194 kilowatt. This much of work you are getting in kilowatt. Then you have to calculate one more net work, that will be in terms of the kilojoule per kg. So it is how much? This is 3360 minus 2520, right? So your value will be, let me do this, 3360 minus 2520. So this is 840, right? So we got this 840 kilojoule per kg, right? Now we need to find out the mass flow rate, right? That is mass rate flow, you can say, that which is mentioned in the question, mass rate flow, right? So whenever mass flow rate we are calculating, that we can denote by m dot, right? And for steam, so yes, so we can say the m dot s is equal to net work W net in kilowatt by W net in what? Kilojoule per kg. Alright, so now you can substitute these values, that m dot s is equal to W net we calculated, which is 1194 by 840, right? So how much? 1194 by 840. So the mass flow rate is 1194, right? So the mass flow rate is 1.42. So it is the 1.42 in what? Kilogram per second. So this much of mass is flowing through the cycle in 1 second. So this is your answer, right? So this is all about the simple steam power plant. So in subsequent classes, we are going to discuss about the Rankine cycle, performance of Rankine cycle, problem we will discuss based on the Rankine cycle, and which thermodynamic cycle, that basically the steam power plant is works on the Rankine cycle. So that we will discuss in the next video. Thank you.